In this lesson, we're going to explore the electrophilic addition reactions of alkenes, focusing on the additions that occur under acidic conditions. Addition is one of the six fundamental types of organic reaction. In an addition, a molecule is quite literally added across the pi bond of an organic reactant. An electrophilic addition is the addition of an electrophile across a carbon-carbon pi bond. So in this example, we have an alkene, and the electrophile is this XY molecule. And you can see that the entire XY was added across that carbon-carbon pi bond, the X being placed on the left carbon and the Y being placed on the right. Now in this example, the relative placement of the X and the Y is actually irrelevant because of the symmetry of the alkene. When asymmetrically substituted alkenes are reacted, a regioselectivity issue arises, because multiple products are actually possible. If we look at the next example, we can see that the two carbons of the alkene are actually differentially substituted. The carbon on the left is attached to two methyl groups, and the carbon on the right is attached to one methyl group and a hydrogen. And that means it's going to matter which group, the X or the Y, gets attached to which carbon of the pi bond. You can see the difference in the two products. In the left product, you can see that the X attached to the left carbon and the Y to the right carbon of the pi bond. In the right product, you can see the exact opposite, the Y attached to the left carbon and the X attached to the right carbon of the pi bond. Those two products are actually constitutional isomers. And in this context, when they're the products of a reaction, we call them regioisomers. When a reaction prefers to form some regioisomers over others, it's said to be regioselective. And as you'll see, some of the electrophilic addition reactions of alkenes are regioselective. Stereoselectivity is another concern for many organic reactions. So if you look at the example here, we again have an alkene that is differentially substituted. In the products, you can see that the X ended up on the left carbon and the Y on the right carbon of the pi bond. But you can see that we still end up with four products. And in this case, those four products are actually stereoisomers. In this reaction, two new chiral centers were formed. And that means there could be as many as four possible stereoisomers formed from the reaction. A reaction that prefers to form some stereoisomers over others is considered stereoselective. And as you'll see, some electrophilic addition reactions are stereoselective. The stereoselectivity in electrophilic addition reactions is expressed in terms of the relative spatial placements of the two groups that were added. If we look at the top two products of this reaction, in each case we can see that the X and the Y were added to the same face relative to one another. In the left product, the X and the Y were added to the top side or top face of the pi bond. And on the right product, you can see that the X and the Y were added to the bottom face. When the two groups that are being added are placed on the same face, it's referred to as a syn addition. In the two bottom products, you can see that the two groups were added across from one another, on opposite sides or opposing faces of the pi bond. So on the left structure, you can see that the X ended up on the top face and the Y on the bottom, and in the right structure, the X on the bottom and the Y on the top. When the two groups that are being added are added on opposite faces, it's referred to as an anti-addition. As we begin to look at the specific electrophilic addition reactions, you'll see that some give only syn products, some give only anti-products, and some give a mixture of both. So the first electrophilic addition we're going to look at is hydrohalogenation. Hydrohalogenation is just the addition of one of the halogen acids, HF, HCl, HBr, or HI. So in this example, I start with a differentially substituted alkene. You can see that the carbon on the left is attached to two methyl groups, and the carbon on the right is attached to two hydrogens. When hydrogen bromide is added across that pi bond, two regioisomer products are possible. In the left product, you can see that the Br added to the left carbon of the alkene and the H to the right. And in the right product, you can see that the H attached to the left carbon of the alkene and the Br to the right. And it turns out the reaction is regioselective, favoring placement of the halogen onto the more substituted alkene carbon. So here I show the reaction mechanism. Remember that when you're learning a new mechanism for a polar reaction, it's a good idea to start off by trying to identify the roles of the nucleophile and the electrophile. In this case, the alkene will serve as the nucleophile. We know that carbon-carbon pi bonds are nucleophilic. and there's nothing electrophilic about that alkene. And that means that the HBr will serve as the electrophile. Specifically, the hydrogen of HBr is electron deficient because of the bond to the more electronegative bromine. So in the first step, electrons will flow from the electron-rich nucleophile, the pi bond, towards the electron-deficient electrophile, the hydrogen of HBr. And that's going to result in the formation of a CH bond. And because that new bond to hydrogen would exceed its valency, we have to push electrons off at the same time, so we push the electrons away from the hydrogen, breaking the HBr bond, and depositing a new lone pair on the bromine. Now, those pi electrons were shared between two carbons, and in this first step, those electrons will end up being shared between one of those carbons and the hydrogen from HBr. And there is an ambiguity as to which carbon those electrons will remain attached to. Again, I like to think of the electrons in carbon-carbon pi bonds as being a door that's hinged on both sides. So if the door opens up so that the hinges are on that right side, then we're going to end up with a CH bond attached to the right carbon. And that's what's happening in this top part of the mechanism. You can see the new carbon-hydrogen bond on that rightmost carbon, and because we pulled electrons away from the left carbon, it's now electron deficient, making a carbocation. If the door opens up so that it's hinged on the left side, then we're going to end up with the new CH bond attached to that left carbon. And that's what's happening on this lower mechanistic pathway. You can see the new carbon-hydrogen bond on the left carbon, and because we pulled electrons away from the right carbon of the alkene, that carbon is now electron deficient, making a carbocation. Now, carbocations have an empty p orbital, making them powerful electrophiles. And regardless of which carbocation forms in the first step, the second step is simply the bromide acting as a nucleophile and pushing electrons in to that empty p orbital to form a new CBr bond. So we saw that the hydrohalogenation is regioselective, favoring the placement of the halogen on the more substituted carbon of the pi bond. And it turns out that many electrophilic addition reactions follow that same pattern of regioselectivity. That regioselectivity can be summarized by Markovnikov's rule. Markovnikov's rule states that any electrophilic addition of an HX-type molecule that proceeds through a carbocation intermediate will favor placement of that X onto the more substituted carbon of the pi bond. So here I have that exact same reaction drawn out now using skeletal structures. And you can see that the halogen ended up on the more highly substituted left carbon of that alkene. Using Markovnikov's rule, we can predict the outcomes of other hydrohalogenations. Here we have 1-butene. Reacting it with HCl is going to form this product here as the major product. Again, 2 regioisomers could have been produced here, one where the chlorine was placed on the left carbon, the less substituted carbon of the alkene, and one where the chlorine was placed on the right and more substituted carbon of the alkene. But Markovnikov's rule tells us that the preferred product will have the halogen attached to the more highly substituted carbon of the alkene. Keep in mind that Markovnikov's rule doesn't always apply. In the cases in which an alkene reacts that has equal but not identical substitution on each carbon of the double bond, you'll actually get a mixture of products. Take a look at this example. If you look closely at that alkene, you can see that the 2 carbons are actually equally substituted. Ignoring the double bond, each carbon of the alkene has 1 alkyl group attached to it. The carbon on the left has a propyl group attached, and the carbon on the right a methyl group. So the 2 carbons of that alkene are equally substituted, each having 1 alkyl group attached, but they are not identically substituted because the 2 alkyl groups aren't the same. Now, because both sides of that alkene are equally substituted, that means that Markovnikov's rule doesn't really help here, and you're going to end up with a mixture of products where the bromine attaches to either of those 2 carbons, in this case giving rise to 2 different secondary alkyl halides. So reactions like hydrohalogenation that obey Markovnikov's rule are called Markovnikov regioselective reactions. But why does hydrohalogenation exhibit this form of regioselectivity? Just about any aspect of a reaction can be explained if we look at the reaction mechanism and the energy changes that occurred during the reaction. Let's first analyze hydrohalogenation thermodynamically. Here we have a free energy diagram of that same hydrohalogenation using 2-methylpropene and HBr. Now remember, thermodynamics is the study of reaction equilibria, and it's tied to the energies of the reactants and the products. And that technically means that the mechanism is really irrelevant when looking at thermodynamics. Remember that the more exergonic a reaction is, the more product it will form. And in this case, we have the potential to make two products from the exact same reactants. And as you can see here, the two products actually have roughly the same energy. And of course, since both products are being made from the same reactants, that means that the reactants in each case have the same energy. So if the two different products have the same energy, and the reactants are the same to make either one, that means that just as much energy is being released in forming the green product, the major product, as is the red product, the minor product. And that means that at equilibrium, the same amount of each product will form. Well, that just means that the reaction is not under thermodynamic control. A thermodynamic analysis doesn't explain why the green product is the major product. And that means that it's not under thermodynamic control, it must be under kinetic control. And that means we have to look at the kinetics of the reaction. Remember that kinetics is a study of reaction rates. And if we do a kinetic analysis of this reaction, we need to know the mechanism, which we do. We know the reaction is a two-step process that goes through a carbocation intermediate. In this case, because the reaction can form two products, it goes through two different carbocation intermediates. And if you look at the free energy diagram, you can see that unlike the products, those two carbocations that lead to the final products actually do have different energies. The tertiary carbocation that leads to the major product is actually more stable, it's lower in energy, than the carbocation that leads to the minor product. And that's because there's a stability trend with carbocations. The more highly substituted a carbocation is, the more stable it is. And that means that a tertiary carbocation is the most stable, then secondary, then primary, and then methyl carbocations are extremely unstable. Because that tertiary carbocation is more stable than the primary carbocation, the tertiary cation will form more quickly. And because the tertiary carbocation is formed more quickly than the primary carbocation, it means that the green product will form more quickly than the red product. And because the green product is formed more quickly, there'll be more of it produced. You could compare this to workers in a factory. Let's say we had a doll factory, and we had two workers, and both of them had the job of making dolls from a big pile of doll parts. Doll bodies, doll heads, arms, and legs. So let's say the pile had enough doll parts to make 100 dolls. And one of the workers worked very quickly, and the other worker worked very slowly. The fast worker is going to create a very large pile of completed dolls much quicker than the slow worker will. And when all of the doll parts are used up, that's it. The slow worker can't work overtime. There's nothing he can do to make more dolls if all the doll parts are used up. So the worker that worked more quickly will have the bigger pile of finished dolls at the end of the day. Because a kinetic analysis of this reaction explains the outcome, it's considered under kinetic control. So in our kinetic analysis of the hydrohalogenation, we actually cheated a little bit. Remember that reaction rate is actually determined by the energy of activation for a reaction, and that's the energy difference between the reactants and the transition state. In our kinetic analysis, we were actually looking at the intermediates and their stabilities and not the transition state stabilities. So how do we know that the two transition states leading to those carbocations show a similar difference in energy? Because it's really the difference in transition state energies that we need to look at, not the difference in intermediate stabilities. The problem is that transition states are transient. Their energies can't be directly measured, and they can't even really be drawn properly because they involve partially formed and partially broken bonds. So how can we compare the relative energies of transition states when we don't even know exactly what they look like? Well, the way we get around this problem is to invoke Hammond's postulate. Hammond's postulate states that in any reaction step, the transition state will more closely resemble the species it is closer to in energy, that is, the reactant or the product. So here I have a couple of free energy diagrams, one depicting an exergonic reaction and one depicting an endergonic reaction. If you look at the exergonic reaction, you can see that the transition state is closer in energy to the reactants than it is to the products. There is a smaller vertical distance between that high transition state and the reactants than between the transition state and the products. And because the transition state in an exergonic reaction is closer in energy to the reactants, it means that structurally it will actually more closely resemble the reactants than the products. If you look at the endergonic example, you see the exact opposite. In this case, you can see that the transition state is closer in energy to the products than to the reactants. And that means that the transition state will more closely resemble structurally the products than the reactants. In either case, the stability of the transition state will be affected by the same factors that influence the stability of what it resembles. So if we look back at the free energy diagram for our hydrohalogenation, we can see that in each case, the first step is the formation of a carbocation. And the formation of the carbocation is endergonic. And that means that the transition state will more closely resemble the product of that step, that is, the intermediate, the carbocation, than it will the reactant. In other words, these two transition states look an awful lot like carbocations. And a transition state that looks an awful lot like a tertiary carbocation is going to be more stable than a transition state that looks like a primary carbocation. And that's why we can state that the transition state along the green path is lower in energy than the transition state following the red path. And that means the green path will be a faster reaction. So we've got two more types of electrophilic addition reactions to look at. The next one is the acid-catalyzed hydration. Hydration literally means just adding water. And if you look at this example, you can see the alkene added water across that pi bond. And you can see that the OH went to the more substituted carbon of the alkene, and the H went to the less substituted carbon. And that means that this acid-catalyzed hydration follows Markovnikov's rule, where HX, in this case the X would be hydroxide, the X ended up bonded to the more substituted carbon. You can see that the reaction produces an alcohol. Now, if we look at the mechanism, you'll see that it closely resembles the reaction mechanism for the hydrohalogenation. The first step in hydrohalogenation was the protonation of the alkene by the strong acid, HBr or HCl, whatever. Those acids were sufficiently strong enough to protonate the alkene, which is actually a very weak base. Now, if you pour water on an alkene, all you're going to get is a wet alkene. And that's because water is nowhere near acidic enough to protonate an alkene, which is a very weak base. The way we get around this problem is by adding a catalyst, specifically an acid catalyst. In the presence of a strong acid, water will react to form hydronium, which is in and of itself a strong acid. And hydronium is a strong enough acid to protonate an alkene. And so the first step here is essentially identical to the first step in the hydrohalogenation, except now we're using hydronium as the acid. So in the first step, the pi electrons push towards the electron-deficient hydrogen of hydronium to make a CH bond. And of course, hydrogen can only have one bond, so the existing HO bond must break. And that pushes a new lone pair onto the oxygen, creating water. And that means we're going to form a carbocation. Well, possibly two, but from here on out, we're only going to draw the more stable major carbocation product. And this is why this reaction follows Markovnikov's rule. The formation of the more stable tertiary carbocation will occur more quickly than the formation of the primary carbocation. So in the second step of the hydrohalogenation, the resulting halide, like bromide, simply attacked the empty orbital of that carbocation, and that formed the final product. In this case, because the acid we have is hydronium, well, the conjugate base of hydronium is water, and so now water is our nucleophile in the second step. Regardless, it's the same thing. Water will now attack that empty orbital on that carbocation to form an oxygen-carbon bond. But as you can see, that doesn't make our final alcohol product. It actually makes the conjugate acid of the alcohol product. And that means it simply needs to be deprotonated. This intermediate is actually called an alkoxonium ion. It's just, again, the conjugate acid of an alcohol. So there's a third step here, and that third step is simply the removal of one of those hydrogens on the oxygen. In this case, it's likely that another water molecule will come around and act as the base. So here we have the electron-rich oxygen of water attracted to the electron-deficient hydrogen of that alkoxonium ion, so those electrons push forwards towards that H, creating a new OH bond, and again, H can only have one pair of electrons on it, so we have to push electrons off at the same time, so the HO bond breaks, depositing a new lone pair onto that oxygen, and that makes the final alcohol product. And if you look closely, the first step involved the reaction of a hydronium ion, and the last step formed a hydronium ion. And that means that overall, acid was not consumed in the reaction. Only the alkene and a water molecule were consumed. And that's why the reaction is catalytic in acid. The acid catalyst enabled the reaction to occur, but was not consumed by the reaction. Similar to hydration, alcohols can also be added to alkenes under acidic conditions. The reaction is essentially the same as the acid-catalyzed hydration, but instead forms an ether. So in this example, you can see that we're adding methanol across this alkene. The reaction is again Markovnikov regioselective, placing the alkoxy group onto that more highly substituted carbon of the alkene. The mechanism is essentially the same as the acid-catalyzed hydration, except this time starting with an alcohol in place of water. Whereas protonation of water forms hydronium, the protonation of an alcohol forms a similar compound called an alkoxonium ion. The alkene is protonated by the alkoxonium ion to form the more highly substituted, more stable carbocation, and then in the second step, that carbocation is attacked by the nucleophilic alcohol, forming a carbon-oxygen bond. In the last step, another alcohol molecule acts as a base, removing a hydrogen from the oxygen and forming the final ether product. In some instances, hydrohalogenation and the acid-catalyzed hydration and addition of alcohol fail to give the expected product. If we look at this example, we have an alkene reacting with HBr. We can see that the left carbon of that pi bond is more highly substituted than the right, so we would expect a Markovnikov addition, placing the Br on the left carbon and an H on the right. When we look at the actual product, we can see that something rather strange has happened. We do indeed see that a hydrogen has been placed onto the rightmost carbon of that pi bond, but the bromine is actually on an adjacent carbon. It didn't even end up attached to either of the carbons of the original alkene. This unexpected product is the result of a carbocation rearrangement that occurs after the initial protonation of the pi bond. Let's take a look at what's happening at the mechanistic level. We know that the first step in hydrohalogenation is the protonation of the alkene to give the more highly substituted, more stable carbocation. In this case, the result is a secondary carbocation. Now, if we look at the carbon just to the left of the carbocation, we can see that that is in fact a tertiary carbon. If the positive charge could be placed on that carbon, it would result in a more stable carbocation. The hydrogen atom on that adjacent carbon migrates onto the existing carbocation in a process called a 1,2 hydride shift. A hydride is simply a hydrogen with a pair of electrons. And when that hydrogen moves with that bonding pair of electrons, a hydride shift occurs. It's referred to as 1,2 because it's occurring between adjacent atoms. That 1,2 hydride shift results in the rearrangement of the carbocation from a secondary carbocation to now a more stable tertiary carbocation. The newly formed tertiary carbocation is then attacked by bromide to create a carbon-bromine bond and complete the mechanism. This kind of carbocation rearrangement can occur from either a 1,2 hydride shift or a 1,2 alkyl shift, the migration of an alkyl group from an adjacent carbon. And these migrations will only occur if it results in the formation of a more stable carbocation. With that in mind, we can predict that a carbocation rearrangement will occur whenever a secondary carbocation would form adjacent to either a tertiary or a quaternary carbon. An adjacent tertiary carbon will result in a 1,2 hydride shift to form a tertiary carbocation, and an adjacent quaternary carbon will result in a 1,2 alkyl shift, again forming a tertiary carbocation. Hydrohalogenation and the acid-catalyzed additions of water and alcohols all occur under acidic conditions, and each of those reactions goes through a carbocation intermediate. The last thing we need to consider for these reactions is their stereoselectivity. And it turns out that these electrophilic addition reactions that occur under acidic conditions and go through a carbocation intermediate are simply not stereoselective. And that means that hydrohalogenation and the acid-catalyzed hydration and alcohol addition will give a mixture of both syn and anti-products. This lack of stereoselectivity can be explained if we break down the mechanism into its individual steps. In the first step, that protonation reaction can occur from either face of the existing pi bond. In the second step, the nucleophile attacks the empty p orbital of the carbocation, and that p orbital has two identical lobes. And because those two lobes are identical, the nucleophile is just as likely to attack one versus the other. And because the initial protonation can occur from either face of the alkene, and the nucleophilic attack in the second step can occur on either side of the carbocation, The result is a mixture of both syn and anti-addition. Now, the stereoselectivity of these reactions only matters when new chiral centers are formed. The addition of HBr to ethane would simply form bromoethane. It doesn't generate any chiral centers, and so the stereoselectivity really isn't relevant or important. If the addition reaction results in the formation of one chiral center, it will simply produce a racemic mixture of both enantiomers. It's only when two new chiral centers are generated that we can actually see the difference between the syn and the anti-additions, and it could result in the formation of as many as 4 possible stereoisomers. So what if we wanted to draw out all the possible stereoisomer products, explicitly showing the configurations of each new chiral center that formed? Well, there are a few ways this can be accomplished, but I'm going to show you the way I prefer to do it. So in this example, we're starting with this tetrasubstituted alkene. As drawn, the alkene is implied to be positioned in the actual plane of the screen. So what I like to do is take the alkene and rotate it 90 degrees in either direction along the axis of the carbon-carbon double bond. So the way I've done it here, that forces the two methyl groups to now be coming out towards us, and it pushes the two ethyl groups to be fading back. Now, what that rotation does is place the pi bond in the plane of the screen. And because the new bonds that we're forming during the reaction are formed by reacting the pi bond, placing the molecule into this rotation guarantees that all of the newly formed bonds will also be in the plane of the screen. So to draw out the two syn addition products, I would simply redraw this rotated alkene without the double bond, and then add the two pieces, in this case H and Br, both to the top face and then once both to the bottom face. I would then do the exact same thing, but for anti-addition. I would redraw this rotated alkene without the double bond, and then add the H to the top on one and the Br to the bottom, and then in the other drawing, place the H on the bottom and the Br on the top. And you can see that this gives us our 4 possible stereoisomer products, with each chiral center drawn neatly with dash wedge projections. Just make sure that when you do this, you're consistent with the regioselectivity. In all 4 drawings, I kept the H connected to the left carbon of the pi bond and the Br to the right.